Okay, so we've gone through the process of drilling a pilot bore, okay, just a narrow diameter hole into the ground. We've got aquifer material, which we've assessed that, we've decided we've got aquifer, we've cemented that pilot bore in place. Before that we did a few tests on it, displacement tests, okay, with the falling head test, worked out approximate hydraulic conductivity, decided everything was okay to proceed. It looks like we have an aquifer, looks like we have an aquifer that's going to move water, hopefully produce lots of it, and so we cemented that in place. Alright, so now it's up to us to basically tell the client, yeah, it's okay, we think you can go ahead, and they'll give us the okay, and then we start designing wells, a testing program, run the testing program, look at the results, and then model it, and hopefully everything after that has gone okay. 9 times out of 10 it works pretty well. The objective of all this stuff here is, like I say, the next phase. This is the major phase of the project. This is where the money really is being outlaid. Is to develop the resource, so design and install wells and odds bores. We need more of these things so we can monitor the groundwater regime while we're testing, okay, which is data we're going to use for modelling at the end. You need to do all this because you have to prove in an RMA application that this is going to be safe and sound. So even though you get to the end of all this, the process doesn't finish. Prove the yield, long-term pumping tests, so taking lots of water out of the ground at the rate we want it to go for a long period of time, okay, making sure that the aquifer behaves itself, and also we will get data from that. We will be able to determine the aquifer properties, transmissivity, storativity, and hydraulic conductivity, which are values we need when we come to modelling the thing. Proving the quality as well. We take water quality tests early on in the process and later on in the process to make sure things are good, the water isn't changing through time, okay, which is really, really bad. And we're going to model the thing to prove the long-term viability, because of course people don't want these things to last for a year, they need them to last for decades, and so we need to hopefully prove that the aquifer will be able to produce the required discharge over an extended time period. That's really, really important. Okay, so we get the client's approval, it's okay, all the provisional items on the contract, or some of those anyway, the drilling, the wells, and again the casing and the screens, all the other bits become active, and the contractors can burst into action again. They really bad the site, because the equipment used in this part of the process is much, much different from that gear that we used earlier, and they get permission to proceed and they go for it. Of course, before they can do all that, they've got to get information from us, because we've got to design the well, tell them how deep to go, what diameter we want it, length of screens, diameter of screens, whether there's any packs involved, where the thing's going to be placed, whether there's going to be more than one well, where the odds bores are going to be replaced, etc. So there's a whole range of things that have to be done before they can actually do anything, and it's got to be done quite quickly, because of course they're waiting to go and it's all costing money. So we know, we've already found out where our aquifer is, right, how deep it is. Maybe how thick it is, don't know. If they're really thick, you might not go all the way through it, you might just be tapping the top of it. Okay. We know what the material is, what the overlying geology is, possibly whether it's a confined or unconfined aquifer, maybe whether it's leaky or not. We haven't determined that because we haven't done the long-term pump tests. Hopefully we know its thickness, but like I say, we might not know that. We've got an idea of the quality of the water, right, with those preliminary tests, but they're not always that great. They generally come up with high iron and manganese levels simply because of the drilling process. The development doesn't completely clean it out, because we've only done that for 2 hours, okay? But there are safety levels, and generally if you get high iron and manganese levels, they will drop through time with pumping, so they're not a big deal. But it's the lack of things like boron and sulphur and arsenic and all those nasties I talked about last time. If you haven't got those, most likely going ahead will be already good. We've got the preliminary K from the displacement testing, so we know it's okay. Generally, as I said last time, the conductivity you get from that displacement test, and sort of my experience anyway, is generally, this is a refractory rock, about an order of magnitude lower than what you get when you do a real pump test. So as long as it's within kilo, you're usually pretty good. Right, we need to design these wells, okay, so we need to consider the required yield that the client wants, how much water they want us to get out of the ground for them. It's a lot, usually it's quite a lot. You're talking about 50 litres a second or more pumping out of the ground for a decent municipal supply or whatever. This will affect the diameter of the final well, i.e. the cost as well, okay, so it's really important to get this bit right. It may affect the number of wells. If you can't get enough water out of one well, you may have to construct 2 or 3 wells. That complicates things as well, okay, because all this gets multiplied by 3 or 4, or however how many wells that you have to make. You need to consider the depth and the diameter to which you want to case the well. Okay? This is really heavy-duty, thick metal pipe, expensive stuff. Okay, but it's really important you get it right, because this will hold the well open over time. Okay, protect seal off the aquifer from any overlying influence, okay? And it'll also protect the pump, keep the pump from being damaged inside the well, so it's a really important thing. Also, got to make sure that it's deep enough so that when the well is pumped and the water inside the well gets drawn down, it doesn't go below the level of the pump. So you have to make sure that it doesn't happen, or the pump can be placed deep enough, right, to stop that happening. It's really important as well. So there's a whole lot of things that you're still not guessing, but you're still sort of estimating until you actually get things up and running, and you need a bit of slot to hopefully accommodate if anything goes wrong. You need to consider the velocity of the water travelling through the well. Okay, it's really important. If the water travels too fast, you get big head drops because of low pressure, you get big drawdown, it's harder to pump. Your well is extremely inefficient, right? So you need a big diameter well because the water velocity up through your well has to be kept below a certain amount. We'll talk about that in a minute. And you need to decide on the length of your screens. Screens are really expensive if you're using good quality screens. One of the most expensive parts of the well. They're important because they keep all the nasties out of it. They protect the pump from getting bits of stuff pieces in it. But you need to consider the water intake velocity through the screens as well, because that also has an effect on the well efficiency and to some degree whether the water pressure drop going through the well will release material that will encrust the screens and block them up. And possibly you may need a filter pack. This is a pack of varying size gravels with nice clean stuff that you actually pack around your screens, okay, to stop material getting in as well. Most of the stuff I'm talking about for you guys is fractured rocks, so you don't need that, but I'll just talk a little bit about it later. Okay, so the casing will keep the well open. It's got to be strong. Okay, the ground squeezing in on the casing is doing a really good job of trying to crush it. Okay, keeps the well open and allows water to reach the surface, protects the pump, etc. Generally, you hopefully case your well down to the top of the aquifer. So everything above the aquifer is completely sealed off. Okay, nothing can leak into other layers, nothing can leak into the aquifer. You've isolated it, which is really important. Okay, then no contaminants, etc. can get in. So it isolates the aquifer from the upper levels. Provides the maximum allowable drawdown as well. Okay, drawdown, we'll talk about this. I'll talk about this later on. We'll talk about the pump testing. But the level inside the well does drop considerably when you pump it. You don't want the water level to fall below the pump level, otherwise the pump switches off and you're wasting your time and you've got a bit of a fail on your hands, which isn't good. The diameter of the well must be able to provide the required yield, like I said, we'll talk about that in a minute, and also fit the pump. Okay, some of these pumps are quite large if you're after large amounts of water and it's coming from quite deep. They're big pumps, okay? A lot of cable in there as well. So it's determined by the purpose of the well and the aquifer characteristics. Municipal supply, you need large quantity of water, so you generally need larger wells to get those out, and you probably need more than one of them as well many times. So for this amount of water, 4,320 cubic metres a day, which is 50 litres a second, that's the magic target that we have to hit. You need a well diameter of about 250 millimetres. Okay, that's completed well, that's not the size of the hole that you put the casing in. The casing itself will be 250 millimetres. You actually drill a bigger well, you drill about a 300 millimetre well to put this casing into, so it's costly stuff. You know, if they wanted less water, you can have a narrower well, drilling costs are decreased, and casing costs, etc. decreased as well. If you're lucky and your aquifer is really good, or you determine it's good, you might be able to do that with one well. And there are many cases we've done that, but sometimes you need more smaller diameter wells as well. I said before, you need to keep the velocity in the well down within the casing, okay, the vertical velocity of the water. It's got to be below 1.5 metres a second, okay, when you're pumping. Anything above that, you start getting turbulent flow, you start getting excessive drawdown, right? You start getting a very inefficient well. It costs lots of money to run for the amount of water you're getting out of it. It's really bad. Casing material must be corrosion resistant, withstanding the collapse pressure of the hull. Okay, so generally you're going to use good quality steel casing. Okay, most of the time it's oil pipeline casing. The strength, there's various designations of the stuff, but there are standards for this as well. Okay, there are actual official international standards for casing. American Petroleum Institute is one of them. Okay, so you get casing like this particular designation here, 5LB. It's basically seamless line pipe, high tensile strength, corrosion resistant, okay, and it's about 10 millimetre wall thickness, so it's really good stuff. It's industry standard material. That's the kind of thing you would stipulate back in the contract, way back in the spec and the specifications. The contractor would have costed that up and put that amount into that contract and the schedule of prices It's important that you determine these things. So all of this has to be determined, certainly materials and things, right, before the project even starts. So you've got to hope you've got it right. Also, the annulus between the casing, because you put the casing into a big hole, right, there'll always be a gap between the outside of the casing and the hole gets fully grouted, cement grouted to the surface, okay, and that will cement the casing in place and seal it away from the ground, okay, helping protect the casing, okay, and hopefully make things last a bit longer. Right, as I said before, the first thing you have to do is make sure that your diameter well will let water be pumped through it at less than 1.5 metres per second for the volume you want to get out of it. Simple calculations to do, okay, they're not very hard. So as I said before, we need a 250mm well to get 50 metres a second, 4,320 cubes a day. Could we do it with a 200-metre well? Save a lot of money, save drilling costs, save material costs, so it's cheaper, okay? The casing and the screens are all cheaper, so everything is cheaper. Well completion overall is cheaper, less concrete to hold the thing in place, so you can reduce the costs. Would it work? Required yield is that, equals 0.05 cubic metres a second, so 50 metres a second. For a 200mm casing radius, okay, 0.1 metres area, pi r squared, 0.31 cubic metres, okay? If we work out the velocity of the water through that pipe, okay, with that surface area and that speed, so that volume for that area, 1.62 metres per second, way too fast, okay, we want to get it below 1.5. We would have an inefficient well, excessive drawdown inside the well because the velocities would be too high, pressure's too low, drawdown too high, pump working too hard, maybe the pump has to be put too deep in the well. Either way, you're overworking the well, it's not going to be good, it's not going to be efficient. So our 200mm casing isn't going to work, okay? Will our 250mm casing work? I don't know, that's just a way of working out. You can read through that when you get the notes. So, 0.125 radius, so 0.049 square metres, okay, area inside your pipe, inside your casing, and 50 litres a second, that gives us a velocity of just over 1 metre a second. Good. That's what we want. We want a bit of slop, we want a bit of leeway. It means that maybe I would actually increase the take from that well and still keep things efficient, still keep everything running nicely. It's really good if you can get that water out. Okay, maybe I'll increase it to 55, 60 cubic, 50 cubic meters litres a second. Sorry, okay, which would be a really good thing, getting the water out of it. But you have got a bit of safety there. Okay, you can't get a 225mm casing, you go in 50mm increments, so there's nothing in the middle. A 250 will be good, that'll do our job for us, it'll keep things safe, it'll keep our well efficient. And first you have to do that, make sure that you've got the right material for what you want. Okay, the pipe's very boring stuff, that's it. Big steel metal tubes, these are seamless, okay, sizes of ones that oil industry standard things. One of the jobs that you will do is to make sure that the contractor is not ripping you off. You will actually inspect these things before they go in the ground. There's lots of things you'll inspect before and as they go into the ground, but first you go on site and you check the casing is of the correct spec. It'll be printed on the side, it'll be a little sticker inside there as well. Okay, you can see reasonably thick stuff, okay, 10mm thick, it's weighty, it's many tens of kilograms per metre, okay, so it's a lot of weight when you've got 200 or 300 metres of this stuff going down into a hole. Also, it will have beveled edges. I'll talk about that in a minute, and that's to do with the welding of the stuff, because of course you weld lengths of this together as you lower it down into the hole, and those beveled edges are really important. I'll talk about this thing in a minute as well. Okay, so then you've got to think about your screens with your filter packs. Right, because the screens allow water to pass the well while keeping solid material out, keeping bits and pieces out. And also, in many cases, if you're dealing with unconsolidated or softer material, keep that bottom portion of the well, i.e. the aquifer, open from collapsing in. Okay? But anyway, they let water into the well and keep foreign objects out of the well. So they're actually a really vital part of the well design. If you're dealing with fractured or cemented rock, you may not need screens. Okay? You may be lucky to be able to get away without them. If you're doing the thing for a long-term project and they want it very safe, you'll put screens in anyway, just in case, okay? Even if it seems it's not necessary, the drillers go, you're wasting your time and money. This thing goes on our time and money, they want to put them in, and so you put them in regardless. It's unconsolidated strata, so generally open fine aquifers or shallow things, then you will need screens, okay? You need lots and lots of them. If it's unconsolidated and poorly sorted, you probably also need some sort of filter pack as well, some sort of artificial gravel pack, okay, of a specific size that will surround the screen, acting as a filter, stopping small particles getting into your well. It's really important you keep foreign object out of your well because they go up through the pump, through the rotors of the pump, destroy the pump, and it won't work very well when pumps aren't cheap. So, the screen length is decided by the aquifer thickness. If you've got a really, really thick aquifer, you may not need to screen the whole thing. You may just need to put a sort of a token screen in there, but it will have an effect. If the aquifer is not overly thick, you might screen the whole thing. You're going to get maximum water going in. You also keep the water traps, the water parts going into the well horizontal, which decreases turbulence. I'll talk about it at the end. But if it's very thick, or you haven't even reached the bottom of the aquifer, and you've got into the andesite down to the climates, for instance, because that's a mountain range and how deep that goes. So we sort of tapped in about 20 metres into the top of it and just screen the top 20 metres. You only screen a small portion, just enough to make sure that you've got the right amount of open area to get the right velocities through the screens so you get enough water. But that has issues because that can affect well efficiency. Again, I'll talk about that towards the end. The slot size of the open area of the screen is decided by the aquifer material. Okay, so I'll show some pictures, but screens have lots of different slot sizes. So if you've got really coarse material or fractured rock, you can use a large slot size. Okay? If you've got a lot of fine material, then you have to decrease the slot size. Decreasing the slot size, of course, decreases the open area of the screens, and so then you have to use a longer amount of screen, a longer distance of screen, to let your required water through at a certain velocity, because the velocity through the screens of the water can't be more than 0.03 metres per second. Otherwise you can have issues. Okay, so you need to make sure that the screen length has enough open area, right, to accommodate that velocity through the screens before it gets to the well. There's all sorts of screens depending on how deep you are, what material you're in. So the cheapest ones are the slot PVCs. Okay, there's glue those together and put them down into your well. You can see the open area compared to the actual closed area is quite a lot less. Okay, so you have to take that into account when you're working out this next thing. I'll talk about screen velocity, because the screens are never 100% open unless you're not using any. Slotted steel, okay, you want something a little bit stronger, and you can see slots take up a very small amount of the overall surface area, so you're not letting a lot of water in with these types of screens. Same with louvers and bridge slots, okay? Same sort of thing. The overall slotted area isn't that big, but they're cheap. These ones are much cheaper than these things. The continuous slot V-wire, which is the best, it's got the biggest open area, very strong, okay? It's all stainless and steel, all well adhered very nicely, but they're very expensive, expensive screens. I say they're really good to work with if you are allowed to use them, because they come in a whole variety of different sizes and diameters for various aquifer types. The wire itself is a sort of a continuous wire that's just wound around these stays and welded in place, okay, and it leaves behind gaps between each row as they weld down. And of course, if you want finer screens, then the gaps between the wire will be finer. If you want coarser screens, then they can adjust that as well. So very versatile. And towards the inside, here, this is the inside of the screen, it's the outside water flowing in. Here, called V-wire screens, this is the V-wires, because they leave a nice gap that gets progressively larger as you go in, so you don't get gravel binding up. If you get little bits and pieces stuck, it'll eventually get washed in and taken out with the rest of the water, hopefully not doing too much damage to the pump, or hopefully that'll happen when you're developing the well anyway and not while you're operating it. So if you've got cylindrical sided slots, then they can quite easily gum up, and once they gum up, you've essentially written those off. If they're not porous anymore, you're not getting water flowing through them. You don't want that to block, okay? You want to make sure your screens can operate cleanly for as long as possible. You can take screens out during the operational life of a well and clean them or replace them, right? But you don't want to have to. It's expensive, and you have to stock your wells, so you've lost your water supply, etc., etc. So the best you can get these things here, but they're very expensive. Right, so slot size. If you, like I say, got fractured rock, as you can understand, it's not pouring into the well, it's holding itself open up quite nicely. You may not need screens, but you may install them for the security of the hole and for the security of the pump. It's probably a wise thing to do, especially if you're looking at having wells operating for many, many decades. Okay, you want to keep things as good as possible. You pay a lot of money to construct a thing, you may as well do it properly. But you can use a large slot size for maximum water, okay, at minimum velocity, keeping it well below that 0.03 metres a second. It's unconsolidated, then the screens are a necessity because they'll have to keep the aquifer open. They'll be supporting it open. The aquifer will fall in against the screens. Again, the water will make its way through the aquifer into the screens. And you determine the slot size by sieve analysis of material. Remember, you've recovered material you have from your pilot bore, so you can take that material, break it up, sieve it, and work out what size, slot size you need. Okay, so I'm not going to go through the process, it's not that vital for you, but you will need filter packs. You will need screens. If the material is unconsolidated and very poorly sorted by a whole range of grain sizes, you may actually need a filter pack there as well. Okay, so this is a gravel pack, okay, well sorted material of a particular size, and you determine that from your sieve testing of the aquifer material. That forms a barrier between the screens and the aquifer, okay, keeping the aquifer material out, okay, stops that finer material being mobilised into the screens. It's very important in some cases, okay, you don't always need it all the time. The drillers will be able to give you a really good idea of what you need as well, okay, because remember often they've been doing this kind of thing for a long time, they've seen a lot of material, they have a lot of experience with different types of aquifers and things too, so they can actually have some input into how you can construct your well, but, so you don't know that until you've drilled at least one hole. Anyway, you take aquifer material, so you sieve it and grade it, and you choose the aquifer, so your gravel pack, depending on the shape of the curve and other attributes of your aquifer. So you do different grain size analyses. This is for very fine sand, this is coming up here for coarse sand and fine gravel. Okay, you're looking at your slot size, which is down here on your grain size. Okay, it's going to determine what size the slots you will use in your screen will be, and you generally look at about 45–50% of the material passing and determine your slot size, so your screen size from that. You can see with these very fine ones, okay, you're looking at extremely fine screens, and so screens with not much opening, very, very narrow slots. Therefore, you'll need very long screens to achieve a velocity below 0.03 metres a second. And as the material gets coarser, you can see that grains, the slot size also here will get coarser as well. Okay, that's pretty much it for those. Anyway, how do you determine whether the velocity through the screens is going to be below 0.03 metres a second? Well, it's easy enough to determine whether the velocity in the well casing was going to be below 1.5, so it should be pretty easy to determine this as well. Okay, so volumetric and velocity calculations, there's nothing hard about it. But anyway, keeping it below that is really good. You want the water to go into the well as slow as possible, okay? Decreases the inefficiency of the well. The low velocities, higher pressure, higher water level inside the well, easier to pump it from a high level to the surface. You can save on pump costs, electricity, etc. Maybe you even be able to use smaller pumps, which are also cheaper to run. Reduces the possibility of incrustation from pressure drop. Remember when your water zips in through the screens, it'll be going faster, okay, but the velocity will increase. When that does, you get lower pressure and it can deposit material on your screens. Iron and manganese being particularly susceptible to that. And it doesn't take long once the screens start getting encrusted to start filling in those slots, thereby making it worse and worse and worse, gradually over time decreasing your well efficiency. That's not a good thing. It increases cost, it makes you have to replace the screens, okay, and or the pump, either one, which you don't really want to do. Okay, we'll take an example of a fractured rock. Okay, we're putting screens in anyway for the long-term security of the pump and the well, just because we're paranoid. What's the minimum length of screen required for our 250 diameter well, pumping out 50 litres a second, 4 a day, using 200 millimetre diameter screens, and the screens want a 40% open area, so very big slots, okay, quite a large open area for the screens. We use narrower diameter screens because the screens get installed down through the casing. Okay, I'll talk about the construction in a minute. So the screens will telescope through the casing, so they are necessarily small diameter because they're going to fit down through the casing. It also means they can be recovered and checked from time if you need to as well. So it's just what is done. You can see the diameter of the screens themselves slightly less than the diameter of that casing that we put in the ground before. So there you go. So it's our discharge, volume, velocity and area. So screen area is going to be discharge over velocity. 50 litres a second, 3 metres a second is what we want to achieve, or less than. Alright, so we'll need 1.67 square metres of open area along our screens to achieve 0.03, okay? Preferably longer, okay, if we want to drop it below that. What are you guys? Hopefully you notice. Okay, so the area of screen per metre length, pi d times 1, so in this case, pi times 0.2, let's turn a little bit of screen, that's 1 metre. So per metre, each length of our screen, if it was fully open, and not slotted,